Okay, in this lecture we're going to finish up our section 2.2 material on vectors in space. So in the first part of this section we had defined the three-dimensional coordinate system, or space, as the set of all ordered triples of real numbers, and we had looked at how to represent points in space and find the distance between points, or spheres in space. So given some of this information, we can now talk about vectors in 3 dimensions. So we're extending the definition of a vector in the plane to a vector in space. And a lot of the concepts and notation that we talked about in section 2.1 will be similar for vectors in space. So let's start by defining a 3-dimensional vector as an ordered triple of real numbers, which is denoted again in boldface as A. And we would write our vector in angled brackets where we have real numbers A1, A2, and A3. And these numbers are called the components of that vector A. Or again, if we're writing vectors by hand, we can't really use boldface by hand. So we would use the variable a with a little arrow over it to denote a vector. And we would write in angled brackets its components, a1, a2, and a3. So similar to what we saw in section 2.1 for vectors in the plane, these 3 components, a1, a2, and a3, indicate how much this vector, or which might represent a velocity or a force, is acting in the x, y, and z directions of space, respectively. Now, there are 3 specific unit vectors, so we're called unit vectors or vectors of length 1, which we would denote as I, which is the vector 1, 0, 0, j, which is the vector 0, 1, 0, and k, which is 0, 0, 1, which point in the directions of the positive x, y, and z axes. And these vectors are referred to as the standard basis vectors. And just like we saw for the standard basis vectors in the plane, I and j, any vector, A, in 3 dimensions, can be expressed in terms of those standard basis vectors, as A is equal to the first component times the vector I, plus the second component of A times the vector j, plus the third component of A times the vector k. So as we had seen in section 2.1 for vectors in the plane, we can represent vectors as arrows that have some initial point and terminal point. And the vector which has its initial point given by A, which is x1, y1, z1, and terminal point B, which is x2, y2, z2, that vector is denoted as AB with a little arrow over it. And the first component of that vector is the difference between the x1 and x2 coordinates for the terminal and initial point. The second component is the difference in the y coordinates of my initial and terminal point. And my third component is the difference in the z coordinates between that initial and terminal point. And any vector whose representation is drawn so that its initial point is the origin is called a position vector. So just as we had seen in section 2.1, let's look at an example where we are asked to find the vector represented by the line segment whose initial point is A, the point 2, negative 3, 1, and the terminal point is B, which is the point 1, 4, 3. And then we're asked to sketch the vector representation of AB and the corresponding position vector. So let's start by finding the components of this vector. So the vector whose initial point is A and terminal point is B is denoted as AB. And the first component would be the difference in the terminal point, or the x-coordinate of the terminal point, which was 1, minus the x-coordinate of our initial point, 2. The second component is the difference between the y-coordinate of my terminal point and the y-coordinate of my initial point. And our third component would be the difference in the z-coordinate of the terminal point and the z-coordinate of my initial point. So altogether here, we're left with -1, 7, 2, as this vector, whose representation is the arrow from point A to point B in space. Now we're asked to sketch the vector representation of AB and the corresponding position vector. So let's see if we can get a rough sketch here. So we have the x-axis, the y-axis, and the z-axis making up space. And the vector from A to B, well, let's start by sketching our initial point A, which was 2. So along the x direction, we're moving outward 2 units. -3, so in the y direction, we're moving in the negative direction 3 units. And z was 1. So we're moving from the origin 2 units in the x direction, and then 3 units in the negative y direction, and then 1 unit upward. So this would be our point A. Let me erase some of my lines here to clean up my figure a little bit. And then let's plot our terminal point, which was B, which was the point 1, 4, 3. So in the x direction, we're moving out 1 unit. In our y direction, we're moving out 2 units. 4 units. And in the z direction, we're moving upward 3 units. So to get the point B from the origin, we are moving outward 1 unit, 4 units in the y direction, and then 3 units upward. So this would be our terminal point B. Again, let me clean up my figure a little bit here. So our vector representation of the vector AB would be this arrow that is moving from point A to point B in space. Now we're also asked to draw the corresponding position vector. So let's see if we can find our position vector. The position vector would be the vector whose initial point is the origin. And to find the terminal point, well, we look at the components of our vector AB. So from the origin, we are moving 1 unit in the negative x direction. We are moving 7 units in the y direction. And then 2 units upward. So from the origin, we move 1 unit in the negative x direction. We are moving 7 units in the y direction, and then upward a distance of 2 units. So let's see, went a little too far in my figure here. But 2 units upward So this would be our terminal point. So again, before I draw in my arrow, let me clean up my figure just a bit. So the position vector corresponding to this vector from A to B would be the same vector, but such that its initial position is at the origin. But these are both representations of the same vector from whose initial point is A and terminal point is B. So these two vectors are equivalent. So let's look at the concept of the magnitude or the length of a vector in 3 dimensions. So we would define the magnitude or length of a vector A in space, whose components are A1, A2, A3, as follows. So the notation is going to be the same as the magnitude of a 2-dimensional vector. We write our vector A in this sort of double absolute value looking symbol known as the magnitude, length, or norm of the vector A. And it's defined as the square root of the sum of the squares of the components of A. So that is the square root of A1 squared plus A2 squared plus A3 squared. Now, just like we had seen for vectors in 2 dimensions, there is only one vector that has length 0 or magnitude 0. It's referred to as the 0 vector and denoted as 0 written in boldface. So the 3-dimensional 0 vector has components 0, 0, 0. And this is also the only vector with no specific direction. So now that we've defined vectors in 3 dimensions, let's talk a little bit about how vector algebra will be defined for 3-dimensional vectors. And as we might expect, it's defined in the exact same way that we had for vectors in the plane. So this theorem I will refer to as some vector algebra. So let's suppose that we have 2 vectors A and B in 3 dimensions. Whose components are A1, A2, A3, and B1, B2, B3. And C is some scalar, so that is some real number. So we can define first scalar multiplication of a vector by a scalar. And it's denoted as the vector C times A, where C times A is found by multiplying each component of A by that scalar C. Vector addition is defined or denoted as A plus B, and the components of the sum A plus B are given by the sum of the components of our vectors component-wise. So that is, the first component is A1 plus B1, our second component is A2 plus B2, and our third component is A3 plus B3. Then our last operation, vector subtraction, is denoted as A minus B, where the components of this difference are defined component-wise. So the first component would be A1 minus B1, second component is A2 minus B2, and my third component is A3 minus B3. And the geometric interpretation of scalar multiplication, vector addition, or vector subtraction is the same as what we saw in section 2.1. So taking a scalar multiple of a vector in space, scales its length or its magnitude and perhaps reverses its direction. The sum of 2 vectors can be visualized either using the parallelogram or triangle laws. And vector subtraction can be thought of as, so the difference, A minus B, can be thought of as A plus the negative of B. So we would reverse the direction of the vector B and then add A to negative B using the triangle or parallelogram laws. So to finish up in this section, let's look at an example where we will perform a few operations on vectors in 3 dimensions. So in this example, we're given the vector A, which is -2, 4, 3, and B, which is 1, 2, -1, and we're asked to find A plus 3B. So we would start here with the vector A, which is -2, 4, 3, and then to that vector, we're adding 3 times B. Now to get 3 times B, we take the components of the vector B and multiply each of them by the scalar 3. So here we would have 3, 6, -3. And adding these two vectors, component-wise, we would have 1, 10, and 0. So this would be the sum of A and 3B. In part B, we're asked to find the magnitude or the length of the vector 2A minus B. So let's start by calculating that vector. So first, we're going to look for 2A minus B. Now 2A is found by taking the components of A and multiplying each component by the scalar 2. So we would have -4, 8, 6 for 2A, and then we're subtracting the vector B, which was 1, 2, -1. So the difference of those two vectors would be the vector -5, 6, and 7. So now to find the magnitude, or the length of this vector, 2A minus B, we would take the square root of the sum of the squares of our components. So here I would have the square root of -5 squared plus 6 squared plus 7 squared, which reduces to the square root of 25 plus 36 plus 49. Now 25 plus 36 would be 61, plus our 49 gives us square root of 110. So that would be the magnitude of that indicated vector. And in part C of this example, we have a problem similar to a problem that we had seen in the previous section, where we're asked to find a unit vector, so that is a vector of length 1, in the direction of the vector A. So just like we did with vectors in the plane, to find a unit vector, we would start by finding the magnitude of our vector A, which would be the square root of the sum of the squares of its components. So here, the square root of -2 squared plus 4 squared plus 3 squared, which reduces to the square root of 4 plus 16 plus 9, or square root 29. So now to find a unit vector, let's call it U, in the direction of A, we would take the vector A and divide each component by the magnitude of A. So here our first component of A was the vector -2, which is then being divided by the square root of 29. Our second component would be 4, and then we're dividing by the square root of 29. And our third component of A was 3, we're then dividing by the square root of 29. So this vector would be a unit vector, or a vector of length 1, which has the same direction as the vector A. Now we could ask similar questions. Well, if we wanted a unit vector in the direction opposite of A, we would then just need to scale this by -1, just reverse the direction of this unit vector. If we were asked for a vector of length 10 in the same direction as A, we could take this unit vector that we found in the direction of A, which has length 1, and then multiply by the scalar 10 to get a vector of the desired length.